Hey, is anybody here who wasn't here yesterday? Again, is there anybody here who was not here yesterday? Show of hands, anybody here who was not here yesterday? I guess they're still dead to us. Oh well. Whoever those people were. I will begin with a word of prayer. So, Heavenly Father, we thank you for this morning. I thank you for your grace to us each and every day, Lord. And I just pray you bless this class, Lord. In your name I pray. Amen. Okay, so as you know, we missed Monday, so I'm trying to catch up in some sense. And so I think the next thing on the list was we're discussing differential calculus, right? I showed you how to derive like derivative of inverse tangent. I should talk to you a little bit about graphing with calculus in case it wasn't emphasized in your previous course. All right, so there's just a couple big ideas we need from time to time, right? This is mostly the application we're interested in is, say, bounding a function. Do you know what a bound for a function is? So if f of x is less than or equal to m for all x in I, so let's say I is a subset of the real numbers, then m is an upper bound for f on that interval I. And likewise, if you could say, let's say little m is less than or equal to f of x for all x in I, then little m is a what? Lower bound. Thank you. For f on I. Now, of course, a function doesn't have to have an upper or a lower bound, right? For a given interval, it could be unbounded, right? If a function has both an upper and a lower bound with respect to some interval, then it's said to be bounded on that interval, all right? So sometimes we need to find such a little m or big M for a function, and one convenient way to do that is with calculus, right? So, application of f prime of x is what? What do we know about, what's the mean value theorem say? Let's say the closed interval a to b. So suppose that we have a function, it's differentiable on a closed interval from a to b, and let's suppose that the derivative exists, all right? Then what can we say? What would the mean value theorem tell us? Yeah. Point on the x-axis where it's equal to the slope. It has something to do with slope. I'll agree. And it also has to do with there exists c in the interval a to b, right? What is it? What? You can ask questions. Fine.
I'm not sure.
It's allowed.
Isn't it like if they're like the same, that there's a point in between where the slope is 0?
That is a good question. That's Rolle's theorem. Yeah, Rolle's theorem says that if you have something that begins and ends at the same point, then at some place in between, there's a place where the rate of change was 0, right? I mean, in this case, y velocity, the marker, right? If it comes up and down back to the same point, there's a point where it turned around, where it has velocity 0. That's Rolle's theorem. Stated in terms of velocity, the mean value theorem says that the average rate of change has to be equal to the instantaneous rate of change at one point. Or that the secant line connecting A and B has to match the slope of the curve at A. So let me just write it down. There exists C such that what? F prime of C is f of B minus f of A over B minus A. So on the right-hand side, that would be the slope of the secant line connecting x equals A and x equals to B to the graph on the graph y equals f of x. And of course, f prime of c is the slope, right? So the picture is something like this, right? So here's your a comma f of a, and over here is your b comma f of b. The secant line connecting these two, something like that, right? And the mean value theorem says that there exists at least one point C. I mean, in this one, you can see a couple different ones, right? Like one choice for C is about in here somewhere, right? So the slope to the tangent line right there is about matching the secant, but there's also another point down here. So it doesn't say that there exists a unique C, but there's at least a C which matches the average rate of change. Yes, sir? Oh, very good. Very good question. So this is my abbreviation for such that. Yeah. So, all right, what does this have to do with boundedness? All right, well, what does this I mean, what does it mean for a function to be increasing or decreasing? Let's talk about that. Because you can talk about the concept of increase or decrease without connection to differentiation, all right? So consider this. I mean, this is the definition. If a less than or equal to b implies, and I shouldn't use a and b here. Let's use something more divorced from the previous discussion. I don't know. Pac-Man, ghost. There we go. If Pac-Man is less than or equal to ghost, and that implies that f of Pac-Man is less than or equal to f of ghost, or f of Pac-Man is greater than or equal to ghost, f of ghost, then what can you tell me about the top option versus the lower option? Which one of those means the function's increasing? Which one of those means the function's decreasing? Yeah. Top is increasing. Very good. And the bottom one is what? Decreasing, right? Now, technically speaking, you notice that increase and decrease concerns what? A pair of points, right? For this to be interesting, they really should not be the same point, right? Pac-Man and Ghost shouldn't be equal. And if this is true for all points in some interval, then the function said to be increasing or decreasing on that interval. All right? Does this have anything to do with differentiation? No, not directly. We can talk about increase or decrease of a function which is just defined on some like just collection of points as opposed to the whole continuum, right? So you talk about a sequence which is just defined for natural numbers being increasing or decreasing with this definition, right? Even though there's no direct notion of differentiating a sequence. So, okay, but think about this. If a function's increasing, right, and if a is less than b, as is assumed here, right, what does it say about the derivative then? So if a is less than b, b minus a is what? Positive, right? And if, let's see here, let me specialize this, a less than or equal to b. So increasing would mean f of b is less than or equal to f of a, right? Which would mean that f of b minus, wait a minute, what did I just do? Like, I'll do that. You gotta watch out for me. That'll be kind of a deal breaker here. So anyway, f of a minus f of b is, I just did it again, didn't I? These details matter, right? Sorry. So let's see here. Right, and then 0 is less than or equal to f of b minus f of a, right? So if this is non-negative and b minus a is positive, what does that tell you about? It's positive, right? So the derivative is positive. Right, but I'm saying that increasing implies that the slope is positive. Now you've perhaps been taught that the slope, that the derivative being positive means increasing, and that's true, but we can derive it from more basic ideas also. Yeah. All right, anyway, all of that just to remind you that the derivative is positive over some connected domain implies that the function's increasing there, all right? Now, so what does that have to do with upper and lower bounds, right? Well, if we could find that a function was, you know, so here's a little theorem, if you will. If f prime of x is greater than 0 on a to b, then what? Then we have that f of a is less than or equal to f of c is less than or equal to f of b for each c in a comma b. In other words, this is nothing, I mean, I'm not telling you anything particularly surprising, but if the function is increasing like this, right, and this is a and this is b, then of course f of a can serve as that little m, and f of b can serve as the big M. So a function which is differentiable on a closed interval with a positive derivative is what? It's bounded. And the same can go for, like, if the derivative is strictly negative. I mean, the derivative could be 0 somewhere. That would just make it constant for a bit, right? Notice that with our definition, if a function is both increasing and decreasing, that means it's constant. If I wanted to not allow for constant, I erase the equality here, and that's called strictly increasing or strictly decreasing. Anyway, long story short, if we want to bound a function, usually a good strategy for us is to just differentiate it and look for places where the derivative is 0, right? And then we can kind of just look at each place where the derivative is non-zero and find out how big the function is on that little interval and kind of piece things together. This is the strategy we'll use as we go on in here. Let me stop talking about this. I hope this is enough to remind you about graphing with calculus. The main idea is that derivative positive, increasing, derivative negative, decreasing, all right? So I'm going to turn the page. We'll come back to this bounded thing when we actually need to bound a function later. So if you'd like, I can do an example now. Is there interest? Yeah? Okay. So let's see here. How about f of x equals x squared e to the x on, let's say, 1 to 10. And let me make it a little bit harder. Let me make that e to the minus x. So what's f prime? What's df dx? We've got 2x e to the minus x minus x squared e to the minus x. So I know places where it can change from decreasing to increasing. So-called turning points of the graph are going to be places where the derivative is 0, right? So to see that clearly, I need to find a formula for the derivative, which is easily understood. And so factoring out this e to the minus x is a good move. And I can factor an x out as well. So that's x times 2 minus x e to the minus x. Right? And from that, I can see that critical points from the function for this function are 0 and 2, right? So critical numbers. Now, we're interested in the interval 1 to 10 in this problem, right? So 0 doesn't matter. 0 is outside the domain of consideration, right? So what matters here is what? Yeah, 2. So we look at, we can look at the derivative, f prime of x, and let's see here. I'll put, here's 2, here's 1. The derivative is 0 here. What happens if you plug in between 1 and 2? Like plug in 1.5, what do you get for the derivative? You get 1.5 times 2 minus 1.5, which is 0.5, right? It's a positive number is the point. So that's pluses, if you like. And then if we plug in 3, we get like 3 times minus 1 times e to the minus 3, which is negative. So this function goes from increasing to decreasing over here, right? And so if I wanted to graph, you can see what's going on. If I start at 1, it starts at, well, what's f of 1? E to the minus 1, yeah? What's f of 10? It's 100 over e to the 10, yeah? What's e to the 10? I don't know. It's big. It's probably 100,000 or something, I don't know. But it's rather large, so 100 over e to the 10, that is, that is very small, close to 0. This is 1 over e. 1 over e is about, so I don't want to make this to scale. I'm going to make this, well, fine. Whatever. Anyway, so we're like this. We get to 2. That's a what? A local maximum. And then we're something like, this is not a good picture yet. This doesn't quite do it justice, right? But it's something like that, right? There's a local maximum at 2. And so if you wanted to find bounds, if we wanted to bound this function, x squared e to the minus x on 1 to 10, what would we use? What's a lower bound? What's an upper bound? Can you tell me? 1 and 2. Well, the bound, remember, it's about the range of the function, not the domain. But I agree with the spirit of what you said, which is it has to do with 1 and 2. I think it has to do with 2, because 2 is like, that's m, right? That's where the max happens. But it's not 2 that's the max, it's f of 2, right? F of 2 should be the upper bound. And what's the lower bound? Again, 10 is not a range value, so that would be where I mean, I agree with you that 10 is where it's attained, but the actual, it's f of 10, right? Little m. So from this graphical analysis, I think it is clear that we have the following inequality. We have that 100 over e to the 10 is less than or equal to x squared e to the minus x is less than or equal to, what's f of 2? Is that 4 over e squared? 4e to the minus 2, or 4 over e squared. So there you go. This function is bounded from 1 to 10, and there is its upper and lower bound, respectively. In fact, those are not just the upper and lower bounds, those are in fact the least upper bound and the greatest lower bound. Those are like the best bounds, the closest, the tightest bounds you can find on this function. Yep. The name of this theorem? I don't think this is a theorem per se. This is a family of ideas. This one? I don't think it has a name either. Yeah. Maybe I should instead say application. I don't know. What do you want? I mean, theorem essentially is a word that means, hey, look at this. So that's all I was saying there. But this is part of a larger idea, which is that if you have a continuous function on a closed interval, it attains a minimum and a maximum on that interval. That has a name. That's the extreme value theorem. And sometimes it goes by the name closed interval test for you guys in Calc 1, right? That's that theorem that says you can check the values of the function at critical points and at endpoints and pick winners and losers. That gives you the minimum and the maximum, right? You were taught that. So I'm just really exploring that idea in the context of thinking about the derivative and drawing a picture. Now, as we go on in this course, sometimes we want to bound a function. Later, we'll also want to perhaps bound the derivative or the second derivative. So like, we don't always apply this idea directly to the function at hand. Sometimes we need to bound a derivative or a second derivative or something else, all right? But anyway, this is something that's at our disposal. We can bound functions using calculus, all right? Yeah.
Doesn't the derivative have to be greater than zero to use that theorem?
Right, so really, we're thinking about this theorem as being applied on this little part Like we're applying this theorem twice in some sense, right? And the increasing part on this little part, and then that theorem again on this part. And so by looking at the value at the endpoints and the critical point, we can pick which one's largest. I let you guys do that. I didn't do it. You guys told me that this and that was the min and the max. But you could also see it from the graph, right? So, yeah. All right, I'm going to go on. So with what remains of today, I'm going to talk about hyperbolic functions and trigonometric functions, all right, and try to explore a little bit about how they're the same, how they're different, see where we get to. I'm not sure how far we'll get. It's okay if we don't get to the end of it. It might continue tomorrow. We got time. I'm not sure I really have anything in the homework that tests you on this, right? So this is more kind of a future-looking comment. I don't know if there's even anything in Mission 1 which is about what we just did. But this will come back in the latter part of the course. All right, so trigonometry. More specifically, trig identities. What are trig identities? We need to know. Well, let's see here. I suppose we start with the right triangle, right? And we have an angle theta here. This is a right angle. So, you know the deal. This is A, this is B, this is C. What do we have? A squared plus B squared equals C squared. This is the Pythagorean identity. And we introduce what's sine? What's cosine? Sine is opposite over hypotenuse, right? So in this case, it's B over C. The cosine theta is A over C, right? So that being the case, we can easily see that what's sine squared? So this means that what? B is equal to C sine theta. This says that that A is equal to C cosine theta. So what's A squared plus B squared equal to? It's C cosine theta, quantity squared, plus C sine theta, quantity squared. But there's a common notation, right, that we use for, so this of course is C squared, C squared cosine theta quantity squared plus C squared sine theta quantity squared, right? Which we can factor a C squared out of, right? And what's the notation that we use for cosine quantity squared or sine quantity squared? We abbreviate that by writing cosine squared theta and sine squared theta, right? But the Pythagorean identity says what? A squared plus B squared is equal to C squared, so what do we have? Right, so thus, for C not equal to 0, we obtain what? Well, you guys just told me. Cosine squared theta plus sine squared theta equals to 1. Very good. And that's why this is called the Pythagorean identity, right? Because it's a simple consequence of the definition of sine and cosine in terms of right triangle trigonometry, as well as the ordinary Pythagorean identity. Now, what other things do we introduce in terms of trigonometry? You remember? We introduce, what's it called? Tangent, right? What's that? Sine over cosine theta. And so, you know, from the, if we divide the Pythagorean identity, we get what? So divide the Pythagorean identity by cosine squared, we get, sorry, I seem to be in reruns. We talked about this yesterday. So when we have a sum in the numerator, can we break it up into a sum of fractions? Is 2 plus 5, quantity divided by 7 equal to 2 over 7 plus 5 over 7? Is 2 fifths plus 5 fifths the same as 2 plus 5? I mean, did I say fifths? I meant sevenths. Anyway, the point is yes, if the addition is in the numerator, we can divide, we can, break it up. I just say that because, well, we don't want Dr. Sprano to come in here and see us do the same with the denominator. That, of course, would result in yelling bad algebra and or pounding on the board. So we don't want that. Never know when Sprano's watching. Sprano's kind of like a math Santa Claus. You have to watch out. He knows when you've been good. He knows when you've been bad, So watch out. Watch out. But yeah, there's the identity for tangent and secant, the Pythagorean identity. So these are, I would say, the entry-level trig identities, right? Everybody knows these. Well, most people know these. What's next level? Trigonometric identities. How about this? Did you know that the sine of theta plus beta is equal to sine theta cosine beta plus cosine theta sine beta? So this is the so-called adding angles formula for sine. Do you know the adding angles formula for cosine? What's cosine of theta plus beta? Huh. I missed what you said. Same thing, but with subtraction. That's almost it. Here, keep the, yeah. I think what you said was right. But okay, you're agreeing. Do you guys know a way to derive the second one from the first? Did you know if you know the sine identity, you can get the cosine identity for free? It's very simple. What you do is you think about differentiating with respect to theta. Differentiate with respect to theta. Think of beta as being a constant, right? What's the derivative of theta of cosine of theta plus beta? It would be cosine of theta plus beta times the derivative of the inside function, right? What's the inside function? Theta plus beta. What's the derivative with respect to theta of theta plus beta? It's just 1, right? So differentiating the left-hand side just gives me cosine theta plus beta. What happens when you differentiate this with respect to theta? You get cosine theta cosine beta, right? What happens when we differentiate this with respect to theta? Right, so there you go. So that's the adding angles formula for cosine. There's also double angle formulas, right? Sine of 2 theta, cosine of 2 theta. What are those? If we look at the cosine of 2 theta, what would that be? We'd get what? Cosine theta plus theta. So in other words, beta is equal to theta, and that just gives us what? Cosine squared theta minus sine squared theta. But then what could you do? What could you do with sine squared? It's 1 minus cosine squared theta, right? By the Pythagorean identity. So if we plug that in, what do we get? Cosine 2 theta equals to what? Cosine squared theta minus, parentheses are your friend, 1 minus cosine squared theta. Right, I've just plugged sine squared theta in terms of cosine squared theta. And then collect terms, what do we got? We got 2 times cosine squared theta minus 1, right? So there's an identity. Okay. So we could maybe put a box around this. This is worth knowing at times. Cosine of 2 theta in terms of the square of cosine. But what else could you do with that boxed identity? You could solve it for cosine squared, right? Well, maybe we should differentiate this before we go on. What happens if you differentiate this? With respect to theta, what identity do you get? Chain rule says what? Minus 2 sine 2 theta. On the other side, what do we get? We get a 4 cosine theta times minus sine theta. So what's this? Oh, check it out. So what we have then is that sine of 2 theta is 2 sine theta, well, 2 cosine theta sine theta, if you like. Here is another trig identity, which is often useful. Right? But neither of these will help us particularly. Like last class, we were stuck on integral of sine squared and cosine squared at the start, right? I put that on the board, it stumped you guys, right? I'm sure there's at least 4 or 5 people in here who could do that, right? So out of cruelty, you did an easier problem on the board, you monsters, right? No? I don't know, maybe nobody knows. Let us remove the mystery. Solve for cosine squared, what is it? Cosine squared theta equals to what? Solve this for cosine squared, what do you get? So we get 1/2. I heard a 1/2 cosine 2 theta plus 1, right? Oh, wait a minute. Yeah, I'm sorry, I'm an idiot. I have to add the 1 first and then divide by 2, right? Order of operations matter, doesn't it? Oh, there it is, though. I don't usually write it this way, though. Typically, I like to write this identity. I don't know why, it's just, it's hardwired. So there's the very important identity to know about cosine squared theta. That is life's blood if you want to integrate, right? Because while you cannot integrate the left-hand side, I mean, you proved that last class, right? Yeah, I think the right-hand side we should all be able to integrate with a simple u substitution, right? The corresponding identity for sine squared is what? I won't derive it, I'm just going to write it down. It's 1 minus cosine of 2 theta. You can see that that's what it has to be, because what should happen when we add these two identities together? Yeah, we should get 1, right? Because cosine squared plus sine squared is 1. So you see that the identities have to match up, but just differ by a sign. Otherwise, you wouldn't recover the Pythagorean identity when you add these. So I'm trying to share with you some of the tricks of the trade I know for remembering these off the top of my head without having to like go to the internet or the textbook or whatever. Like, you want to know these things, right? It's like your girlfriend or boyfriend asks you what their pet name is, and you're like, oh, let me look it up. It wouldn't be good, would it? No, these are like pet names for calculus. Like, you need to know these. These are things you should know. All right. I'm sorry. Yes.
Quick question. How'd you get from the sine squared theta equals to 1 minus cosine squared theta to the, it's on the other board over there, to the cosine 2 theta? So the but.
Oh. So minus a minus gives me plus. So I get a cosine squared theta plus a cosine squared theta, which is 2 cosine squared theta. And then that's the minus 1. So,
Oh, okay.
yeah. Mm-hmm. So in summary, algebra. But all right, so these are some of trig identity's greatest hits. There are more, right? There are more. So to do much more, I usually introduce students to something called the imaginary exponential. And you can take it or leave it, all right? But I find this to be very helpful. And so this is the imaginary identity. E to the I theta is cosine theta plus I sine theta. I mean, if you want to solve quadratic equations, the imaginary number I enters in whether you like it or not, right? So if you want to simplify a discussion so that it's kind of like one size fits all, it just seems like complex numbers come into play. That's also true for trigonometry. So this is so-called Euler's identity. And if we look at this, e to the minus I theta, well, that's cosine of minus theta plus I times the sine of minus theta. But what do we know about sine and cosine? Are they even functions? Are they odd functions? What can you tell me? Like, what's cosine of minus theta equal to? You're like, I don't know. You just define sine and cosine in terms of right triangle trigonometry. What do you mean minus an angle? Well, I'm assuming that you've had a larger discussion of sine and cosine. You know well that it extends past right triangle trigonometry. In fact, we define polar coordinates and define sine or cosine of any angle, any real angle in radians, right? And one of the things we learned there is that cosine is an even function and sine is an odd function, right? So that means we got cosine theta minus I sine theta. I can pull the minus out of sine, but the cosine eats the minus. What happens when you add these two identities together? So if you look at this and you add, what happens? This I mean the I which squares to minus 1. It's the square root of minus 1, right? That I. So what happens when I add these? Do you see it? We get what? 2 cosine theta? But how about the sines? They cancel, right? Exactly. So this gives us a formula. Cosine theta is 1/2 e to the I theta plus e to the minus I theta. This is how we can express cosine in terms of imaginary exponentials. What would happen if instead of adding the equations, I subtracted them? What would you get? Now the cosines are canceling, right? And we get I sine theta minus a minus I sine theta, which is? Yeah, 2 I sine theta. So therefore, sine theta is 1/2I e to the I theta minus e to the minus I theta. So these formulas I'm boxing at the moment, these show you how we can think about sine and cosine in terms of imaginary exponentials. Now you might say, I don't know what an imaginary exponential is. Well, fair enough, but do you really know what sine and cosine are? Do you really know what the ordinary exponential is? Not really. You haven't constructed these things from base principles. So take it on faith that this makes sense. You already take a bunch of other stuff on faith in here, actually, if you start thinking about it. And if you will take on faith that these things make sense, and you'll believe me when I tell you that, well, you already know. I'll do it over here. What should e to the I theta times e to the I beta be equal to? This should be e to the I what? Yeah, just theta plus beta, that's right. So this would be cosine theta plus I sine theta. That would be cosine beta plus I sine beta. This would be cosine of theta plus beta plus I times the sine of theta plus beta. Do you know how to multiply complex numbers? You were taught this. You may have forgotten it, but you do. You just have to multiply like usual and remember that I squared is minus 1. Right? So what happens when we multiply this out? We get cosine theta, cosine beta, minus sine theta, sine beta. Why the minus? Because when I multiply this term and that term, it picks up that from the I squared being minus 1, right? And then I have I times what? Cosine sine, and then sine cosine. So here I'm just expanding the left-hand side. So an important thing to know about complex calculations is when we have a complex equation, how much information is in a complex equation? Like, it's not just one equation in some sense, it's really two real equations, right? Because in order for a complex equation to be true, the real part has to match the real part, and the imaginary part has to match the imaginary part. What the real part matching the real part in this equation I just wrote down is what? Can you see it? This is the real part of the left-hand side. This is the real part of the right-hand side. What is that? Oh, that's nothing more than the adding angles formula for cosine. How about the other one? How about the imaginary part of both sides? If we equate this imaginary part to that imaginary part, it's exactly the adding angles formula for sine. So you see, the adding angles formula for sine and cosine, they're both hidden in a natural way inside just the plain old law of exponents for imaginary exponentials. Now it's weird, right? Because I'm saying that the imaginary exponential involves sine and cosine. That's kind of perhaps a new idea. It's very likely a new idea for you, right? I don't know. Personally, I was very excited by this when I first saw it. It also allows you to derive trig identities, which would be otherwise kind of hard to find. So can you guys integrate? let's apply this technology to something kind of non-obvious. So what if we wanted to find the identity for, say, sine of 2 theta times the cosine of 4 theta? What if you wanted to integrate that? Could you integrate that? I think it's tough, all right, without trigonometry. So here's how I do this. I'm like, okay, well, I need to understand what that is. And so what I'm going to do is I'm going to use my handy-dandy imaginary exponential technology, if you will, to derive a trig identity. And so what is sine of 2 theta? Well, that's 1 over 2i e to the 2i theta minus e to the minus 2i theta. What am I doing? I'm using the boxed formula for the sine on the far board, substituting in 2 theta for the angle. All right? How about the cosine? Cosine e to the 4i theta plus e to the minus 4i theta. Now, how can I simplify this product? So the point is I use the boxed formulas to convert to exponentials, because once I have exponentials, I just do algebra by the laws of exponents, which actually still make sense. The proof that they still make sense is actually on the board over there. It's because this imaginary exponential notation is just a really sneaky notation for all of the trigonometric identities which are known for sine and cosine. I mean, that's kind of the proof of it. But, you know, we don't have to prove things. We can use them here sometimes, and that's what I'm doing. So we have 4i, and what's e to the 2i theta times e to the 4i theta? It is e to the 2 plus 4 is 6i theta, right? And then I'm going to do the ones that give me a minus, so I get minus e to the minus 6i theta. Let me do some color coding so you can see where that's coming from. This and this gives me this. This, ooh, contrast of red on red, not so great. Let's see here. And then this with that gives me that. What's next? How about the this guy times this guy gives me what? Minus e to the 2i theta. And then these two gives me what? Plus e to the minus 2i theta. Then the way you play this game is you use the boxed formulas on the right board to convert the sine and cosine to exponentials. All right? You do your algebra. And then you remember that sort of the door to go back to the real world, if you will, is those boxed formulas again. We have to go back the same way. So you have to use your imagination a little bit. This is 1 over 2 times 1 over 2i, e to the 6i theta minus e to the minus 6i theta, right? Minus 1 over 2 times 1 over 2i, e to the 2i theta minus e to the minus 2i theta, which is, by the way, 1/2 sine of 6 theta minus 1/2 sine of 2 theta. And you can always do this. If you have any product of sines and cosines, you can convert to imaginary exponentials, do the algebra, rearrange terms, and write it as a sum of sines or cosines as appropriate. If I tried to teach you how to do this in terms of the things we were doing at the start of class, it can be done. There's a way to do it, but I just find this to be much more easy. Now, the integral of sine theta, sine 2 theta. Now, if you want to learn the trig identities to do this without the imaginary exponentials, you're welcome to do that, right? But I think this is a nice way. So 1/2 integral of sine 6 theta minus the sine of 2 theta. And what is the answer? 1/12, well, minus 1/12 cosine of 6 theta plus 1/4 cosine of 2 theta plus a constant. There you go. Yep.
So you're using imaginary numbers to replace the u substitutions. You don't have to use u substitutions. You're turning a multiplication into a subtraction.
Well, I don't think u substitution is the right tool for these kind of trigonometric integrals. I mean, to do trigonometric integrals, we have to somehow manipulate the expression to things we know how to integrate. So imaginary exponentials just give me another tool to derive trig identities. That's it. You don't need to use them. We could behave as we were at the start of this class and just, you know, derive sine squared plus cosine squared, adding angles. The adding angles formulas can be derived from the law of cosines if you look at the right picture. Now, the other reason that I like to talk about imaginary exponentials is it helps emphasize the shocking similarity between hyperbolic sine and cosine more thoroughly. See, because what we're going to talk about tomorrow is that the definition of cosh x is what? And the definition of sinh x is this, right? So what I'm going to do tomorrow is I'm going to show you, that cosh and sinh are really aptly named. They very, very much resemble sine and cosine. They're not the same, all right? But look at that. I mean, that formula in hand, it's much less, in some sense, surprising the imaginary exponential thing. I mean, there's still something deeply shocking about the imaginary exponential idea. All right? Which is probably only fully explained when you take complex analysis. Of course, you all take that, right? You're like, I don't care if it's not on my DCP. I want to have all of the math that I can do at this school. I want to get my money's worth, right? I'm gonna take a communications class or something online, so I have time to take that complex analysis class as a junior, right? No? All right. Or no, what am I saying? You'll be math majors. You'll all be math majors, yes? No? All right. Well. Oh, I think my time is up. So, thanks, guys.